Okay, so we're going to have a look at building the nucleus, and in particular look at the masses of the different parts of the nucleus before they're assembled into a nucleus, and compare that with the mass of the nucleus once it is a nucleus, and hopefully draw some surprising conclusions. So remember, when we're measuring nuclear particles, we've got an atomic mass unit, which is just a really small chunk of matter, 1.66 times 10 negative 27 kilograms. We're going to have a go at looking at Neptunium-239, and Neptunium-239 is 239.052931 atomic mass units. And so when we're assembling a Neptunium nucleus, we're going to use neutrons and we're going to use protons. And if we look at the nuclide symbol for Neptunium, we can see that there's 93 protons. And so that's going to be 93 lots of the proton mass. So the mass of protons that goes into forming the Neptunium nucleus is 93.739071 atomic mass units. Do the same for the neutrons. So we get those two masses, the masses of the protons and the neutrons, and so we can add those together to get the total mass of the nucleons needed to make the nucleus. And we get a mass of nucleons of 241.004161. And so we immediately leap to the nucleus and compare it, and we notice straight away that we've actually lost approximately 2 nucleons along the way as we've assembled that nucleus. And so that allows us to calculate what we call the mass deficit of the nucleus. So we've got a mass deficit of 1.95123 atomic mass units. So notice that right up until this point we've been working in atomic mass units. Now though is a nice time to convert that number into kilograms. So by multiplying by the 1.66 times 10 to the negative 27, we get a mass deficit of 3.2390418 times 10 to the negative 27 kgs. What we can do with that is calculate the total binding energy of the nucleus using Einstein's E equals mc squared equation. And we get 2.915138 times 10 negative 10 joules, which doesn't sound like very much, but then remember we're used to comparing energies in electron volts, so let's convert that over to electron volts by dividing by 1.6 times 10 to the negative 19, charge of an electron, and we get lots. Lots and lots and lots and lots and lots of electron volts. But what's going to be a more useful number for us to use in this situation is how much energy was there per nucleon, like how much energy, how much binding energy was there per nucleon. Well, we can just divide that number by the number of nucleons, which was 239, and we get 7 million, which is a good time to introduce a new unit. We're going to say 7. Let's round it, 623 mega electron volts. So when we're dealing with these nuclear energies, we find that the electron volts just too small to be of any use. When we're calculating these energies, we're working in mega electron volts, like millions of electron volts, which gives us an idea, a feeling for the kind of energies that we're dealing with when we're dealing with nuclear transformations. Around about 7 million times, 10 million times-ish, as much energy as a photon of light. We're going to talk about, we've just had this idea of binding energy. We're going to talk about what that binding energy means later. This is just how you calculate it.